today. There's really going to be 4 presentations. First, Terra Vigilis, which is an environmental service group that has done this kind of research all across the United States, who conducted the testing, will be sharing the results. And that is going to be the main portion of the presentation, and it'll be the first hour of presentation. And then we're going to have a panel discussion. We had some local divers that actually were under the water watching and feeling what happens when a wake surf boat goes over the top of them, and they will tell you about that experience and what they saw and what they felt. And then we have a new piece of equipment, live scope technology, which also shows the turbulence that's happening down under the water. We did testing of many different types of boats, and we will be sharing the results of those different boats. And then lastly, we're going to share some of the results from the Minnesota study, the St. Anthony Falls Lab, which is some very good results that came out last month, and they have implications specifically to Lake Beulah, and we will cover that as well. So first up, we will have Terra Vigilis. They've conducted science-based environmental studies for various lake associations and municipalities around the country over the past 7 years. They utilize aerial and submersible drone technology to visually capture and present images and video and evaluate the wave impact to the shoreline, lake bottoms, and aquatic habitat. This morning, Tim Thierry and Charles Lubke will present the findings of the study that has been conducted here on Lake Beulah. So please welcome them.
Thanks, Tom. Thank you for having us join you. We're going to take about 45 minutes here and go through some somewhat technical information. Thank you for asking us to join with you this morning. Can you hear me in the back now? Better? Better if it's close? Okay.
Is that better?
Yeah. I can still learn. So again, thanks for having us join with you. My name is Tim Thierry. To my left is Charles Lubke. In the back is another investigator on our team, Mike Mortensen over at Carroll University. And sitting immediately to his right is Howard Caney, who heads Terra Vigilis. We have a security division and an environmental services division. So this is the environmental services group. We're going to have about 45 minutes of material here that walks you through what you need to know about this growing problem in the United States. It's an explanation of the technology associated with the vessels that are used, as well as their impacts, both easy to see, seen impacts, and unseen impacts, things you don't see that are happening under the surface. Will be available for questions at the end. Thanks in particular to the Protect Lake Beulah organization, as well as the Lake Beulah Management Group, for retaining us and supporting us. We've had great support by your members in these two organizations. We use this phrase on most of our published material and completed engineering studies. Science informs public policy. We are committed to that idea, that when you craft public policy that has impact on human behavior, it ought to be based on reasonable considerations for something that are settled. So one of the things you'll hear me say throughout our presentation here is there's a great deal of consistency that is now being shown in the varying studying groups across the country that are looking at this. That's very important in science, that you keep seeing the same thing. So without further ado, let's tell you again, I'm going to talk about the current scientific and engineering studies which have established that there are very significant displacement wave impacts specifically by wave enhancing boats in surf mode, which is a particular operation, to both the surface that you can see and to the subsurface of freshwater lakes all throughout the United States. And specifically, we looked at things here on Lake Beulah. I'm going to talk about 8 primary areas in this presentation. To begin with, the way these vessels are designed and engineered. Okay, sometimes just seeing something and understanding something, you can go, of course that would be a problem. So we're going to talk about how they're made, what they're designed to do. 2, we're going to explain to you some of the physics of wave dynamics. There will not be a half-sheet quiz. We'll talk about surface impacts. We'll talk about wave attenuation buffering distances, a snazzy way of saying how much standoff distance should be used to protect the shoreline or another vessel from a big wave. We'll talk about subsurface impacts, so things you don't see to the lake bed, to the water column, etc. Then we're going to talk specifically about propeller downwash, sometimes referred to as slipstream. So what happens with this energy source that is pushed down by a propeller? We'll talk about nearshore impacts. And then finally, we'll make some references to sediment redistribution, so lake bod composites that are stirred up and kicked up into the water column and what that does. So that's what we're going to cover, and we'll try and do it within a 45-minute window. A couple of definitional things. These are legal definitions that you should just all be aware of. These have been used in various states across the country now who are passing local ordinances or state legislative statutes controlling, limiting, or outright banning the use of wakeboard boats in surf mode on freshwater lakes. So first of all, a wake boat is a motorboat that has one or more ballast tanks holding large amounts of water, ballast bags, or other devices used to increase the size of the wake, so specifically ballasted to produce a big wave. Wake sports, legally defined. To operate a wake boat with ballast tanks, bags, or other devices or design features to increase the size of the boat's wake, or to use a surfboard, wakeboard, hydrofoil, or similar device to ride on or in the wake directly behind the wake boat, with or without a rope, directly behind a wake boat, when the wake boat has ballast tanks, bags, or other devices engaged as described in Section 1. So obviously you can see this was written by an attorney. There is a concept known as a wake sports zone. Why is this important legally? Because in many jurisdictions across the United States, they have communities going, okay, we understand that this is having impacts that harm the lake, but how do we create a spot for these vessels to operate safely that doesn't have impacts? And so they've come up with this concept, a wake sports zone, an area of a lake, pond, or reservoir that has a minimum of 50 contiguous acres, at least 500 feet from a shore on all sides, in at least 20 feet of water, 200 feet wide. In some states, Vermont is one, we've helped the state of Vermont, they've passed at the state level legislation banning the use of wakeboard boats in surf mode, except in wake sports zone areas. They have an app on the phone where the operator of one of those vessels can know if he's in the right place or not, assuming they know how to use a phone. Okay, so let's talk a little bit about the engineering of these vessels. The engineering associated with a contemporary wake boat is designed to increase or enhance the height of a wave, and it shapes the wave for wake surfing operations. The boating industry has focused upon very high engine power, vessel pilot, controllable ballasting so they can move the water around in the ballast tanks, hull design, speed controls, and a wave shaping series of technologies that accomplish that. That's a manufacturer's photograph on open source on the internet. So it's not We've had people say, well, you photoshopped that. That's not true. We don't make stuff up. We're very careful about the things we say. Okay, specifications for the wakeboat engines, power plants. Typically, the engine system on a current day wakeboat is an inboard V-drive to fit into the V-hull configuration. It's designed to accommodate that deep V-hull. Most often, the engine is near the stern, not always, but most often it's near the stern, adding to the weight, and it drives the propeller underneath the hull. The wakeboat horsepower range is 250 to 630 horsepower. 250 to 630, trending upwards. I'm an aviator. I fly airplanes. A twin-engine airplane has engines, a light twin, has engines of about 600 or 700 horsepower on each wing. These are huge engines in these vessels. Mastercraft, a supercharged engine available on current day models. The power plant can produce 630 horsepower or 665 foot-pounds of torque, and that's what's depicted here. That's what the thing looks like. Great big engine. The bottom left is a Volvo Penta inboard-outboard engine, as might be seen on a water ski boat. This particular one is 250 horsepower. If you look at the manufacturing literature, as we did, to give a fair statement about what they recommend for horsepower ratings, anywhere from 200 to 250 horsepower is considered ideal to pull a water skier. So a significant difference in power plant. That's the first takeaway that I'd like to leave you with. Significant difference. Hull design. That's, again, a manufacturer's photograph or image of one of the Mastercraft wakeboard boats with a V-hull designed to produce large displacement wave by sitting very deep in the water, so it's pushing water away as it moves. Next slide, please. The wave enhancing devices. The panel on a current day wakeboard boat looks like the inside of a complicated airplane. It's computer driven with a flat screen where the pilot of that wakeboard boat can select a wave shape, move the ballasting weights around as they're underway. So they can design a wave. Typically, the control surfaces that help them do that include plates, wedges, foils, gates, and very specific control of the speed of the vessel. So when you see a wakeboard boat, they don't go fast. They don't plane out like a ski boat. They sit up with about a 15-degree bow angle off the water, with a stern plowing through the water at about 8 to 10 miles per hour. The ballasting control systems in the current models are under the flooring of the vessel, allowing more people to stand inside the boat, adding more weight. Again, they can control the ballasting pumps and move the water around to help shade a wave. This is a typical wakeboard boat in surf mode. They're easy to identify. You sometimes hear people saying, well, it's very hard to legislate this because you can't distinguish one boat from the other. Patently untrue. It's very easy for a law enforcement officer, a boat patrol officer to go, that's a great big wave produced by a wakeboard boat in surf mode. Charles, who teaches part-time physics, is going to talk just a little bit about wave physics and the dynamics of waves that are occurring surface and subsurface and how they work.
So the waves that you see on the surface do dissipate over distance, right? But what happens, sorry, Tim, can you just step to the side? What happens though is that there is a lot of energy also subsurface that you don't see. So when you see a swell or a peak, there's actually elliptical water movement below it. and it typically is half the wavelength of the distance of the boats. So when we see waves that have a wavelength of 20 feet, so from crest to crest, the depth that the water is having water movement, the wave, the energy that's subsurface, is typically half of that, or 10 feet. So now as the wave that you see on the surface approaches shore, if you think about particularly like on the ocean, as the water gets shallower, the wave gets pushed up from the bottom, and so you get a taller wave, and eventually it breaks and crashes on the shore. Well, where's that energy coming from? It's all the subsurface energy that's also moving. And when I get to roughly half the length of this wave, so if the wavelength is 20 feet, which is typically what we see for a lot of these boats on inland lakes, when I get to 10 feet depth, I'm starting to scrub or be affected by the bottom. And so that water is moving in, it's hitting the bottom, it's increasing the height of the wave, and so all that material that potentially sediment or any aquatic plants are being heavily affected as it gets into the shallower area. Next slide. Just do this. Okay, so we've done a series of studies as well as other organizations across the Midwest. Out in Idaho, there's some big reservoirs and rivers that also have a lot of wake surf activity, and the East Coast. And so you see these large displacement waves or surface waves, and so the impacts that they have to shorelines, to other vessels that are on the water have been conducted. We're going to see more from University of Minnesota later. We've done work at North Lake, just half an hour north of here, Lake Warramug out in Connecticut, as well as here at Lake Beulah. There's an organization called Water Environmental Consultants, WEC. They've done a lot of work out on the East Coast and southeastern United States, and then Western Colorado University also. As I mentioned, Lake Payette in Idaho. Next slide. So one of the things that is, this is probably the most technical graph you're gonna see. This is showing the wave height of a wave that's coming into shore. And so the first one is a wake boat in surf mode. The second one is a jet boat. Basically, it looks like a conventional IO boat, but it's got, instead of a conventional inboard-outboard prop motor, it's got an actual equivalent of a jet vortex engine, and then a typical inboard-outboard boat. And what you see is the peak height is 6 inches above nominal, or a total of 12 inches of the wave height, and this is with the wave starting 200 feet from shore. And so we did a comparative on each of those. And for what we would consider a typical IO or runabout or power boat, it's 3 inches in height, or a total of 6 inches. So the height difference is essentially 2 times the wave height. What's significant about that is when you double the height of a wave, you actually increase the amount of energy in the wave by 4 times. It's essentially the square mathematically, but you can see it visually here. So if this is the height of a wave, if I double the height, I've got 4 times the amount of water that's being moved or propagated. Next slide.
So trust your senses. People make judgments based on all kinds of things, what they hear, graphs, tables, numbers, and images. So we do a lot of drone technology, aerial and subsurface. These are drone images over North Lake as a bird would see it. So the drone is at about 400 feet above the surface of the water. And we put this up so you can see another way of understanding what's just been described about the wave physics. So on the top right-hand corner of this slide, you see wakeboard boat waves coming in with a rather large distance between the crests. That's very different from the waves that are produced by a speedboat, a much shorter distance, about half, just to look at it, and a jet ski, even smaller. We're not telling you anything you don't know that you haven't seen with your own eyes. We just want to capture it in a way that it's difficult to argue with when you get in front of people that have got a bias that says, we're not doing any damage. We don't believe anything you say. I mean, this is a hard thing to argue with. Next slide, please. This too is a hard thing to argue with. So this is Lake Beulah with several passes by a wakeboard boat in surf mode. So here's the boat, high bow angle, stern is down, producing a large displacement wave at the traditional buffering distance from shoreline in most states, 200 feet. So I would invite you, as we play the video, to watch. We'll get to it. To watch the boat as it passes by, and remember that the operator of the vessel typically is not looking behind to see what they've left behind. They're looking ahead. So behind them is a wave, and watch as it propagates in. Again, 200 feet from shoreline, surf mode, wake boat. Here's the wave, energy coming in. All of what you're seeing here is on the surface, not subsurface. We'll talk more about that in a minute, but here it is. Again, if you live on the lake, you've seen these things. You get the idea. Stand by one, just stand by one. At point of sale, the retailers will tell somebody who's buying one of these that doesn't have this sort of background, this doesn't make a wake any different than any other boat. Don't worry about it. You're going to hear people tell you it's doing damage. It doesn't do anything different than other boats. Patently untrue. I'm sorry, go ahead.
Is it possible to talk at the podium since you're blocking out?
Yeah, sorry. You're telling me I'm not good enough. I've heard that at home. So now this is a 4-quadrant view of the same thing, and now we're going to compare a wake boat, a conventional IO, a water ski boat, a jet boat, and an IO boat in transition. I'll talk about transition in a minute. So same video from the wake boat, top left. Directly below it, IO boat. These are all timed to be the same time sequences, so you're seeing real time the differences, and the differences are significant. Again, we're not telling you anything you probably have not seen. Next slide. Now we're going to go all the way out to 500 feet. 500 feet is a distance that has been recommended in a number of states in the country for the manufacturing industry to use, and for local ordinances and state statutory language to protect shorelines and people and other vessels. So this is a 500-foot distance out from the shoreline on Lake Beulah. Wake boat, ski boat, jet boat, IO boat.